Hello, everyone. Good morning, good afternoon, and good evening. Since you're all joining from different locations, different countries, and different time zones. So, I'm Navyasri, Customer Success Executive at Spectransys, and we'll wait a few more minutes to let join the people, and we can start with our session. Thank you for joining. So, hello, everyone. So, we'll wait for 3 more minutes to join the people, and then we can start with our session. Thank you for joining. So, thank you everyone for joining. I think we are good to start. And once again, good morning, good afternoon, and good evening, everyone, since you're joining from different locations and time zones. So, I'm Navyasri, Customer Success Executive here at Spectransys. So, welcome to today's session Understanding Rotor Whirl and Precision. So, before getting started with our session, I would like to give a small intro on our company, Spectransys. And I will be hosting you today along with one of the greatest speaker and instructor, Mr. Subbarao Ganti sir, lifetime experience in the field. And so let's get started with our session. Spectransys is a technological driven company, and our only vision is to bridge the skill gap and help aspirants to find the right opportunities and also connect employers to the right talent pool. And we enable success by providing trainings and also innovative solutions that empower individuals and also organizations to achieve their goals. And our only goal is to empower core professionals. As you see here, the word core, which refers to condition monitoring and reliability engineering, which suits to our profession. And how are we going to do that? So, we offer trainings and certifications to enhance and develop skills to every aspirant, and all under expert guidance. And we also provide career assistance which helps aspirants to learn and grow and find the right opportunities. Along with this, we are also connect employers to the right talent pool. And along with this, we also provide networking so that people come together as a community so that they can share knowledge, their skills, and resources. And to cope up with the current scenario, to boost our knowledge, we Spectransys is here to help you. We prepare you for your success and by enhancing and reshaping your skills by providing trainings, conducting webinars and seminars, and also conferences. And coming to our top core training programs are condition monitoring, which includes ultrasound analysis, thermography, vibration analysis, and other technologies, asset reliability, and this is a great growth path for asset reliability advocates to become leaders. And maintenance management, which includes shaft alignment, dynamic balancing, and bearing. Oil and wear particle analysis, which includes field lubrication analysis, wear particle analysis. Along with this, we are also offering non destructive technologies and some of the mechanical engineering designing courses. And our principal partners, we are the exclusive partners to the industrial press. All of our books are printed by the industrial press. You can visit our website and purchase all our books. And our principal associations are Mobius Institute. And coming to our delivery model, we provide instructor led courses. You can come to our training center and join our classroom and have the trainings. And we also provide private and on site courses. We can have the instructor at your premise to save your precious time and money. And we, along with this, we are also providing online video courses that is self learning method. And the main point comes here. How can we add value? Like why to choose Spectransys? So our instructors are the industry practitioners. Like every of our instructor is having decades of experience in the field, so you can get the better experiences and the best guidance. And we support learning in your own way, as you see our training delivery model. So we have flexible training delivery model and all these under the best price to continue your learning. And also along with these, we are also providing consultancy services beyond the training to solve critical problems to the organizations. And we are the pioneer in the training delivery. As you see, our instructor, Mr. Kotia Nayak, who started all these trainings and certifications in India. And as a part of our commitment to elevate your career, we also built an application that connects every aspirant and also employer. Like this ecosystem is a gateway to career your success and talent pool. By this connection, we create a win-win scenario for the both parties and we enable individuals to find right opportunities and also connect employers with best talent pool. All you can do is create an individual account which is completely free of cost. And I would like to suggest to explore this application right after this webinar. And I'm excited and happy to share that we are hosting a biggest conference ever happened in India. That is Core 2025 for our core professionals, which is happening in the month of July on 25th and 26th. So the main outcomes from this conference is sharing best practices and knowledge. You can meet and learn from the industry leaders, and this is a great opportunity for your advancing your career and also networking. You can get to meet to the peers and employers. So I would like to suggest to go through our website to know more details and get registered today. And thank you for listening to me. Thank you for your patience and time. You can reach out to us anytime through any form. We are available and we are here to help you. So from now, our speaker is going to take over. So, Subbarao sir, over to you. Thank you. And
Thank you.
yes, sir.
Thank you very much. I'm sharing my screen. Is my screen visible to everybody? Is audible? Am I
Yes, sir.
audible
Your
to
screen
everybody,
is
please?
visible. Yes, sir.
Right. Thank you very much. Okay. Uh, Good evening, everybody. And as I was told that this is a webinar organized by Spectransys, and the title of this webinar is Understanding Rotor Whirl and Precision. I am Subbarao Ganti, the speaker for this webinar. And a small introduction about myself. I'm basically a trainer and consultant having more than 35 years of work experience in vibration analysis, troubleshooting and training of industrial rotating machinery. I have served in reputed organizations like NTPC, L&T Massibus in India, and GE and Qatar Gas in Middle East. More than 1,000 engineers got trained under me on this vibration analysis subject here. This is a small introduction about myself. The basic idea in providing this webinar, as you can see on this outline here, to provide you this concept of rotor whirling. When we are looking at the turbomachinery analysis, one of the more important phenomena that happens on the machines when compared to the other rotors which are mounted on rolling element bearings, the rotors are subjected to whirling action. So how to visualize this whirling action and then relating that whirling phenomena to the critical speeds, understanding them from the undamped critical speed map to get an idea about the visualization of the whirling. And then most important of thing, especially the concept of precision. This concept of precision is important, especially those people who are familiar with the vibration analysis of the turbomachinery using orbit and orbit analysis, FFTs, that is full spectrum, waterfall. That full spectrum is one which consists of this important, the precision information is provided in that one. So first you understand what exactly precision is and how to interpret that information from the various plots that the system, that the vibration data generates there. And then with respect to that, you try to understand some machinery malfunctions that basically are influenced by this rotor precision in interpreting their behavior there. So that's going to be this 45 minutes talk about this one. So actually, when you're returning here, primarily the rotor vibration data collection and analysis, you can classify it broadly under two categories. One thing is rotors mounted on rolling element bearings, where you are doing the casing vibration analysis. And the other one is the rotors mounted on fluid film bearings, where we're using the proximity probes there. Now you can see here, whirling is significantly experienced by rotors mounted on the fluid film bearings. And precision is related to this whirling motion. And this is basically in comparison to the rotor spinning direction and plays very important role in analyzing some machinery malfunctions. So on the screen, you are seeing on the left side, the animation is basically the data collected from the casing vibration of the machines mounted on rolling element bearings. And you can see the right side, on the right side animation, you can see that the rotor is simply running around, rotating there without any whirling action. Whereas the rotors mounted on the journal bearings or the fluid film bearings, they execute a different movement there. So the shaft centerline itself is executing a movement apart from the rotor rotation. So this rotation of this shaft centerline movement that is basically related to what is called as the whirling action there. Now on the picture which you are seeing here, this is a picture which depicts a rotor with two discs. And then the basic imbalance that is existing on the rotor is the one which rotates the rotor and provides the centrifugal force. And then while the rotor is rotating at certain speed, you can also see that the shaft of the rotor is also moving around. So that movement of the shaft is called as the whirling orbit here. So the rotor experiences basically two motions simultaneously. One thing is the first rotor is spinning on its axis at certain speed. That is normally the RPM of the rotor, either in clockwise or anti-clockwise directions there. The second thing is the axis of the rotor itself is whirling predominantly under the influence of the residual unbalance force, either in the clockwise or anti-clockwise directions there. So the two motions are happening simultaneously. One is the spinning of the rotor and the other is spinning of the axis of the rotor itself. Now further, this whirling might be the same speed, that is the speed at which the rotor is rotating, frequency. In such a case, this whirling action is called as a synchronous whirl. So the whirling frequency is also equal to the rotation frequency, that is synchronous whirl. Of course, there can be cases where the whirling frequency can be different from the spinning frequency. So that is called as a non-synchronous whirl. Typically, when the rotor is experiencing a phenomenon like oil whirl, so you'll have a subsynchronous whirling of the rotor there. So this is the principal understanding of the whirling motion of the rotor there. And actually, this whirling motion is principally seen at the bearings. While the entire rotor is experiencing the whirling motion, most of the time we are not interested, or we cannot measure that one or visualize that. But when we measure the movement of the rotor within the bearings itself, that's where you try to get here. And when you are measuring at the bearing, it is basically called as the orbit. So this animation helps you to really visualize. You can see that this turbine rotor is rotating, is spinning in one direction, and the axis also, which is shown in the red direction here, that is also experiencing a whirling movement here. So these are the two simultaneously happening movements there. So this is basically the rotor whirling, which is predominantly present in machines mounted on fluid film bearings only. So in rotor dynamics, the study of the nature of the rotor whirling before, at, and after critical speeds and their respective mode shapes plays an important role in understanding the rotor vibration behavior. That's where this whirling phenomena is principally studied by the rotor dynamics engineers there. So what critical speeds basically are nothing but the natural frequencies of the rotor. And you know that natural frequencies are governed by the mass and the stiffness of the rotor as well as the bearing system, which is mounting there. And the damping present in the system primarily controls the rotor vibration response at the critical speeds excited by the residual. So how much is the whirling that is going to happen principally is decided by the damping present there. So this is a picture of a critical speed map. Critical speed maps are often cataloged graphically in what is called as this is an undamped critical speed map. Fundamentally, the idea of these things is to illustrate the relationship between the support, that is the bearing stiffness, and the critical speeds. So how the bearing stiffness is influencing the overall critical speed of the rotor assembly. And then also to tell us at which speeds to avoid during the operation. Once you identify the critical speeds, you should be able to avoid those things during the operation, or if the machine is running at them, you should minimize their time of activity. So on the graph which you are seeing here, on the x-axis is the bearing stiffness and the y-axis is the critical speeds. So at different bearing stiffnesses, you are plotting the critical speed. For example, there are three curves that we are seeing on the screen. One is a black one, the other one is the red, and then the green. The black is the first critical speed of the rotor, red is the second critical speed of the rotor, and the third green one is the third critical speed of the rotor there. You can see that as the bearing stiffness is increasing from left to right, these critical speed values are also increasing. And after certain stiffness of the bearing, the critical speeds are relatively independent of the bearing stiffness at the fag end of the graph that you are seeing there. That is the case for the first two critical speeds, whereas the third critical speed from the beginning itself, it is fairly independent about the bearing stiffness, except extremely on the right side there. So why I'm trying to show you this one here is because the whirling action is also is fundamentally coming up because of the difference in the stiffness variations that is happening here. So this is an animation which is going to tell you about the rotor whirling typically at the critical speeds. So you can see that on the right side of the animation you are seeing, the pink dotted line is the axis of the rotor. And on the extreme right side, you can see that the whirling is happening. It is happening in the clockwise direction. And then the path described by the whirling, by the axis, is typically elliptical here, elliptical orbits there. So at this particular critical speed, the rotor is experiencing significant whirling movement. And this is what we are going to look at and study about that. So the rotor response at one of the critical speeds and the corresponding whirling motion is what you are seeing here. Actually, in practice, a rotor applied in the turbomachinery is basically supported on fluid film bearings, which add anisotropic fluid film conditions to the rotor. Means if you are measuring the vibrations in the X plane and the Y plane, the stiffnesses are not equal in the two of the planes. So that is called an anisotropic fluid film. That is, the fluid film creates variation in the stiffness there, and obviously tries to two different measurements, two different responses on that one. So the non-isotropy of the support stiffness coefficients is responsible for the different rotor whirl motions along the two orthogonal planes, resulting in an elliptical whirl. And also the non-isotropy of the oil film bearing stiffness also responsible for the forward and the backward whirl of the rotors there. So that's the reason we are speaking about the stiffness variation here. Now, when the whirling is considered here, how do you interpret that whirling here? Actually, when the whirling action is happening either in circular or elliptical, in order to create, when a rotor is experiencing a whirling motion, either circular or elliptical, the whirl orbit can be constructed by assuming two vectors rotating at the same speed, that is the same frequency, but it in opposite direction. For example, on the screen, you are seeing a circular whirling movement, and this can be assumed by created by two vectors of equal magnitude, because the orbit is circular, two equal magnitudes and rotating in the opposite direction. One is for this picture I'm showing you as the forward one, which is going on the anti-clockwise, and the clockwise is shown as the backward one here. So when these two vectors are rotating at the same speed, the resultant of these two vectors, if you join the tip of the resultant of these two vectors, that will trace a path, and that path is nothing but the circular orbit which you are seeing here, or the circular whirling movement that you are seeing here. So whenever the whirling movement is generated, it is created by assuming a couple of vectors which are rotating with the same frequency but in opposite direction. Now, if the amplitude of the two vectors are the same, then the whirl will be circular. But when the amplitude of the two vectors are different, then the whirl will be elliptical. And the two amplitudes can be different when we have two different stiffnesses here. And this is going to give you a better idea about the so-called backward and forward whirl, how it is going to come. Now, actually, when you have these two vectors, forward and backward vectors rotating there, on the left side, you see the forward whirl vector here. So when the forward whirl vector amplitude is greater than the backward vector amplitude, then the resultant of those things will come up as a forward here on the screen, which you are seeing here. So this is your forward whirling movement, which are the circle whose amplitude is higher, whose radius is bigger than the backward whirling here. So one is rotating in the clockwise and the other is rotating in the anti-clockwise. Since the forward component is bigger than the upward, the resultant of this is, you see the orbit here, and see this the direction of the orbit. If you see the orbit, it is moving in the same direction in which the forward vector is moving. that is in the anti-clockwise direction. So the forward whirl comes into picture when the forward component is amplitude is bigger than the reverse component. On the left, on the right side of this picture, here you are seeing the backward component is having higher magnitude than the forward component, and the resultant of these two is going to be an ellipse with the rotation in the backward direction here. These are the two extreme cases here. So actually, mathematically, while I'm trying to show you on the pictures here, mathematically this can be arrived because of the stiffness variation between the two. On the graph here, you are seeing the x stiffness and the y stiffness, y plane and x plane stiffness. If they are different, they can give rise to, because of the two different stiffnesses, they try to give you two critical speeds. One with the lower stiffness and the other one with the higher stiffness there. And then the magnitudes of the forward component and the magnitude of the reverse component can be estimated from the mass of the rotor, the eccentricity of the rotor, and then the operating speed in relationship to the critical speed in the x direction and the critical speed in the y direction there. If these, I'm not going to discuss much on the mathematical expressions here. I just provide them to give you an idea about that. But what I'm going to tell you here is whether the whirl is going to be forward or whether the whirl is going to be reverse fundamentally depends upon whether the forward magnitude is high or reverse magnitude is high. Magnitude is going to be high or the reverse vector magnitude is going to be high depends upon these relationships here. So next slide, you can see that when the rotational speed of the RPM is situated below this frequent critical speed, which represents the horizontal critical speed. If it is below, then there are three conditions there. Once the operating speed is less than the lowest critical speed, or when the rotational speed is situated between the two critical speeds, that is the horizontal critical speed and the vertical critical speed, or in the third case, when the rotor speed is operating about the two critical speeds there. These are the three situations which the rotor can visualize. So when these things are happening, the forward whirl will come into picture when the magnitude of the forward vector is greater than the magnitude of the reverse vector. That is in the first case. So in the first case, when the operating speed of the rotor is less than both the critical speeds, then it will generate a forward whirling till the first critical speed is reached. And when the operating speed is greater than the two critical speeds, then again you will come across a forward whirl. But when the operating speed is between the first critical speed and the second between the horizontal critical speed and the vertical critical speed, then the reverse vector is going to be larger in magnitude, and then the rotor is going to experience a reverse whirl or a backward whirl there. So this is how it is going to happen. So on the graph you are seeing here, bearing asymmetry basically is going to give rise. So this is the critical speed in the x direction. This is the critical speed in the y direction. Y stiffness is higher than the x stiffness. So as long as the rotor speed is less than the x critical speed, you are having a forward whirl orbit. And then when the operating speed of the rotor is greater than the two x critical speed and y critical speed, then again you are having a forward whirl here. And when the rotor operating speed is in between these two critical speeds, that is the x critical and y critical speed, then the rotor experiences a backward whirl. This is typically called as the split critical. This is basically called as a split critical, and this phenomena can be experienced on certain machines. Not all machines may show significant change in the x plane and the y plane, but those rotors which has significant difference in stiffnesses in the x plane and the y plane, they can experience this backward whirl very momentarily. Let me tell you, gentlemen, the rotor is not going to spin in the backward direction for a long time. It will be a fraction of a second or something by the machine. The time crosses from this x critical speed to the y critical speed. In between them, there will be a momentary backward whirl appearing there. So that is about the precision about the rotors. That is about the whirling of the rotors. So the rotor can whirl in the forward direction or in the reverse direction there. So, and whether the rotor rotates in the forward direction or the reverse direction again depends upon the operating speed in relation to the critical speed at which is operating there. So having said that, now when these rotors are whirling, and when we use the word precision, now let us understand what exactly precision is. Basically, the slow movement of the axis of a spinning body around another axis due to a torque to change the direction of the first one. So what is happening is, on the right side, you see the animation. There's a disc spinning about a vertical axis, and the vertical axis is also moving there. So the movement of the vertical axis is basically called as the precision of the rotor, means that axis is spinning. Similarly, here in the bottom, you see the turbine rotor whirling. This whirling is also nothing but the precision only. Why I introduce the whirling first? Because that is the first thing which we normally study there. And the precision is an extension description about the same whirling action. Normally, people are interested in the rotor dynamics. The whirling is interested with respect to the critical speeds, whereas the precision is normally seen at the operating speed itself. Now, let us have more clarity on this concept of precision here. So, this precision can be what is called as the forward precision and the backward precision. So, the direction of rotation of the rotor and the orbit, or that is the whirling action, are the same, then it is called as the forward. On the left side animation, you see that the disc is rotating in the clockwise direction, and then the disc center is also whirling in the clockwise direction. That is the forward precision. Both are in the same direction there. On the left side, you see that the rotor is spinning in the anti-clockwise direction, and the center of the rotor, that is the whirling movement, is happening in the clockwise direction. So this is a reverse precision that is happening. Frankly speaking, this reverse precision for the rotors on normal industrial machines, which we normally see, our turbines, steam turbines, gas turbines, centrifugal compressors, and all those things, they don't experience a full-time reverse whirl in their normal thing. Only under certain abnormal condition, there will be a momentary reverse precision of the rotor center there. Let me give you a more idea here. So when the axis of the rotor is stationary and the rotor is rotating, there is no precision here because the axis is not exhibiting any movement here. But the rotor is rotating and the axis is also exhibiting. This is basically, in our vibration terms, we call it as the orbit. Orbit is the visualization of the rotor centerline movement in the bearing. Actually, because we are not able to see the entire rotor whirling along the length of the axis, we are able to only view the rotor axis movement in the bearings in the form of the orbit here. So basically, the precision and data information can be extracted from the orbit, which is nothing but the shaft centerline movement within the bearing there. So for example, if you see this one here, if you think that the outside, this is a bucket with a water and a mug in there in that one. So if the bucket you think is a bearing, and then this mug is the shaft here, the shaft is slowly rotating in the clockwise direction, and you can see that the mug center is also moving in the same direction here. So this is basically the forward precision or the forward whirling of the rotor there. And actually, I'll show you a video where actual reverse whirling, you can see it on a full time, but this is seen on an experiment here. You can see that. Here you are seeing a very long rotor. You see that the direction of the rotor spinning is anti-clockwise, and the shaft center is also moving, the whirling in the anti-clockwise direction. Visually, this is a forward whirling that is happening now. Now, these people will set this into the reverse whirling. Now, you see that. This rotor is exhibiting a complete reverse whirl, a reverse precision. The direction of spinning of the rotor is counterclockwise, whereas the axis of the rotor is spinning in the clockwise direction. Here you can see that. This is your reverse position of the reverse whirl exhibiting on the rotor there. This is not normally seen on our machinery, but that's a very highly, what I should say, is abnormal situation for the machines. Now coming back to the precision. So precision is the lateral motion or the vibration of the rotor geometric center in the x and y planes, that is in the two planes there, which is perpendicular to the axis of the rotor. The precision is also known as the orbiting. That is because of the orbit is what is trying to give us an idea about the precision here, and it is the display of the lateral movement of the shaft center line. So precision can take place even if the rotor is stopped, and it is completely independent of the rotation. For example, if you see here in this particular picture, see if the rotor is spinning on the anti-clockwise direction, but the shaft center is constant here. So the rotor, there is no precision of the rotor here. Whereas on the other side here, the rotor is not spinning. Rotor is not spinning, but the shaft axis is rotating in the anti-clockwise direction. So this rotor is experiencing a precision here. So this is basically idea about the precision. Now, how do you identify the precision? How do you give the direction? Normally, for the precision, we don't use the word clockwise or anti-clockwise. We try to identify the precision with respect to the probes. X to Y probe, the precision is in the direction of from X to Y probe or from Y to X probe. And if the direction of rotation is also in the same direction, then we call it as the forward precision or in the reverse precision here. So the precision is normally mentioned with respect to the probe. X probe to Y probe is the direction of the precision. So how do you identify it here is that, and the direction, how do you get it? It is that information comes from your key phasor information there. So when the normal orbit is happening without any key phasor dot on that, it looks like an elliptical one. So you cannot say in which direction the orbit is moving, either in the same direction in which the shaft is rotating or opposite one. But once this key phasor information is available and if you use that one, then you can try, that will help us to identify whether the rotor precision is forward or reversed, or from X to Y or Y to X, whatever it is the case. So what is the key phasor basically? You know that many of the people who are working on this field know that the key phasor is basically a sensor which is going to give you a once per revolution pulse for measurement of the phase readings here. So the once per pulse is given by this one here. So this is when the projection is there, it's a negative going pulse. When the keyway is there, it is going to be a negative going pulse. When the projection is there, it is going to be a positive going pulse here. So the distance between two consecutive pulses is equal to the time taken for one rotation. And so this is how the key phasor is going to generate reference pulses for the rotation there for phase measurement. So this is an extended understanding of. So when the key phasor is firing, when the keyway is in key line with the key phasor, you see not the voltage dips, and then once the keyway is closing, the voltage goes up, becoming negative and more positive. So when the voltage is becoming negative at the mid-center point of it, that is the triggering level. So that's the time when the key phasor fires for your phase measurement there. So this is going to be the timing event. This timing event, when projected onto on the vibration data. So on the top, you are seeing the green waveform is the vibration coming from a sensor. When the key phasor event is superimposed, the bottom is the key phasor event. When the key phasor event is superimposed on the time waveform, so the starting of the key phasor event will show up as the gap, and then the ending of the key wave event will show up as a spot. So the gap and the bright spot is the direction in which the keyway is moving. So, or in which this shaft orientation, the shaft whirling is taking place, or in which the shaft center line is moving. So the key phasor dot and the blank spot, this is the one which is going to tell you the direction in which the whirling is taking place here. So when you superimpose this on the orbit here, so the blank and the bright concept has come from when the data was being used on the oscilloscope. When you have an oscilloscope screen which is illuminated there, and the X vibration data is fed into the X probe of the oscilloscope, and the Y vibration data onto the Y connection there, and then the z-axis is given the phase information, then the key phasor information on the screen which will appear like this. So when the keyway is going negative, when the keyway is firing, you'll have the blank, and when the keyway is closing up, then you have the bright spot. So this is the event is starting with the keyway blank and then the bright there. So this is the way in which the shaft center is moving. So the whirling movement of the rotor is in this fashion here. So it is going from X to Y. So X to Y is from black and bright, and this is the direction in which the shaft is orbiting. So in this direction, it is the precision is from X to Y. Now, in which direction is the rotor rotating? The rotor is also rotating in the same direction. Then it is called as the direction of precision. It's a forward precision there. So this is how the key phasor will help you to, without the key phasor, if you are having an orbit, will be simply like an ellipse or a like that. And you cannot identify in which direction the rotor is whirling. Once you superimpose the key phasor signal onto the orbit there, then the orbit will tell you. From that one, you can map out whether the rotation, whether the precision is clockwise or anti-clockwise, or the same information I'm trying to show you here again. When the proximity probe is observing a hole or a keyway, it is a negative trigger pulse here. When the negative trigger pulse is coming up, initially you will have a blank and then the bright, and the movement of the curve or the movement of the shaft center line or the direction of precision is in this way. This is in this clockwise direction. Similarly, when you are having a projection on the shaft, the key phasor is looking at a projection on the shaft, then you have a positive going pulse. The positive going pulse will generate a bright spot first and then the blank spot later there. So then this is in the direction in which the orbiting is taking place or the precision is taking place. So when you want to interpret the orbiting direction there, you should first know whether the key phasor is looking at a notch or the key phasor is looking at a projection. In 99% of the cases, the key phasor looks at the notch only. So if the key phasor is looking at the notch, then your direction of the whirling will be from blank to bright. But if the key phasor is looking at a projection, then the direction of orbiting will be from bright to blank. You should keep that in clarity. So now, when you want to describe the precision of this X and Y probe here, now I'm starting my journey from the blank and the bright. So because the key phasor is looking at a keyway, so the direction of the movement of the rotor is from blank to bright. So blank and bright, so rotor is moving in this fashion here. So when the key phasor is firing, the blank and the bright event on the Y probe is at this location, and the blank and the bright probe is at this location. So this is the starting point for the rotor rotation from our point of view. So at this point of time, the vibration at this point, the Y probe has already crossed the peak. And at this is at the negative peak here. So from here onwards, the rotor is orbiting, and then at this instant of time, the X peak came first. Then the Y peak came. So the vibration now the precision direction is when the first peak is coming. So X probe is coming first, then the Y probe is coming there. So the direction of the precision is from X to Y. And if the rotor is also rotating in the same direction, then it is going to be a forward precision there. So this is how you try to identify from the orbit. You can identify in this fashion, or from the time waveform, you can say, looking at the two peaks, which peak is coming first after the key phasor has fired. So that peak the orbiting will start from that peak. In this particular screen which you are seeing, X peak is coming first, then the Y peak is coming. So the the precision is from X probe to Y probe. So this is the direction of precision. And if the rotor is also rotating in the same direction, then this will be a forward precision. So that is about the concept of the precision and how do you identify the precision of your whirling motion of the orbits using the key phasor there. Now then, what is the application of these precisions in the machinery in the vibration analysis? Precision helps to evaluate the whirling direction of the orbit of the rotor, whether forward or reverse there. Under normal machine vibration behavior, most of the rotors is expected to exhibit a forward whirl only. And some machinery malfunctions like rubbing and some other things like exhibits momentary reverse whirl. So the direction of the whirl is identified through the orbit and the full spectrum plots. So orbit I have already explained to you. Now let us look at the full spectrum here. Now on the screen you are seeing a full spectrum waterfall plot of the startup of a machine, and the machine ran for some time and then they shut down here. So for those who are familiar with the full spectrum, what you can see is in the middle axis, that is the zero, the right side information is called as the forward components, forward frequency components, and the left side component, they are called as the reverse frequency components. Now in this particular waterfall picture, you are seeing the reverse components. The reverse components are on the higher side compared to the forward components. So from the concept which we discussed till now there, it appears that the rotor is continuous while the rotor is starting up, and while the rotor is running for some time, and while the rotor is shutting down, it is continuously exhibiting a reverse whirling movement there. So from the full spectrum, this is what you can draw the conclusion. And many people who don't understand the real picture about this one, they think that it is a big malfunction on the rotor there. Especially when you see this type of picture, what a full spectrum, the continuous reverse precision of the rotors there, this is physically not possible on the machine. This is a gimmick generated by some data when the X and Y probes of the data are swapped. For example, the X probe from the field is connected to the Y probe on the 3500 rack, and the Y probe on the field is connected to the X probe on the 3500 rack there. So then the data that you are going to take up, and when the full spectrum generated from that plot will come up like this one. When you see such type of activity here, you can safely conclude that this is typically a data generated by reversal of the probes connections. So when you get an opportunity to stop the machine, because under normal running condition, you can't disconnect the probes there. It is not safe to do that. So when an opportunity is there, the machine shuts down, you go to the field and you check whether the X is connected to X or not. Definitely you will find out that the probes have been swapped either at the junction box or at the rack itself there. So this is even though this data is suggesting a full reverse spectrum there, reverse precision, this is not physically possible. That's why I kept this as the first slide to give many of the people who think that this is a serious mistake that is happening on the rotor. No, this is a mistake which is coming because of the probe swapping only. Next. This is the data taken from a compressor. It's an integrally compressor say the stage in 5-6 had some high vibration tripping there. So this is the full spectrum coming from, on the left side is one from stage 5, I think, on the right side is stage 6 or so. So when the machine is normally running here, you can see that the vibration amplitudes up to certain speed or the amplitudes are very low. And then after the machine is tripping, and when the machine is coasting down, on the if you are looking at the cursor on the right side here, you can see that at certain speed, the amplitudes of the vibration forward components have drastically gone up. And at the same time, you can see some reverse components also coming into picture. And at the same time, on the forward and the reverse side, you can see some harmonic content coming into picture. This harmonic content is not existing before and after that high spikes there. So this is typically a situation generated by the rubbing of the rotor. When the rubbing of at this point of time, when the machine tripped for whatsoever reasons, while it is coasting down, at certain locations, the rotor was rubbing at certain locations there, and that rubbing action has created this harmonic content. You can see that it did not exist before the rubbing. It existed only while the rubbing is happening, and when the rubbing is finished up, you see that it is not existing there. And then here also you can see the forward components and reverse components that are coming here. Now, once you should understand from on the right side plot here is, initially the reverse components are small. You can see that if you are seeing the cursor on the screen, at this point of time, the reverse components are small. And at this, when the rubbing is happening, the forward components are very high, but the reverse components also are increasing here. Now, when this reverse components is happening, what you should see here is the reverse precision is not happening. Whatever is the orbit, when you see that when you have an orbit which is shape is changing from slightly elliptical to more elliptical and all that, that elliptical, the orbit is becoming more elliptical, then the reverse component starts to rise. So this simply indicates that when the rubbing is happening, the orbit shape is changing. When the orbit shape is becoming more elliptical, in order to create that high elliptical orbit, the reverse components are coming into picture. But that it doesn't mean that the rotor is having a reverse precision and this event here. The precision is not, the precision is forward only because the forward components are on the higher amplitude. What is only these reverse components raising their head only suggests that the orbit shape is becoming more elliptical at the event of the rubbing happening there. So here I'm showing you a Bode plot of the machine shutdown here. So on the top you are seeing the orbits. There you can see on the left side, this is orbit 1, 2, 3, 4, and 5. Orbit 5 is captured at when the machine is in the operating condition. You see a fairly circular orbit here. And at certain speed in between, you can see that it slightly became elliptical. And these three orbits, that is orbit 3, 2, and 1, they are captured at this critical speed event here. So you can see this is the split critical here. So one is lower speed, one lower critical speed, and the higher critical speed. When these events are happening, you can see that the rotor shapes are changing. This is where when the time then the precision is not fully changing, but you can see that the orbit shape from the circular, it is becoming more elliptical. When the orbit is becoming more elliptical, if you look at the full spectrum, it will show you higher reverse components that are coming into picture there. Still, the rotor will be having only a forward precision, but the reverse components amplitudes are increasing because the rotor shape the orbit shape is changing here. So this is the filtered condition here. Now in this case, I have shown you that the orbit 1, 2, and 3, 4, 5. So 3, 4, and 5 are taken at this situation here. So 3 is taken when the speed is around 1000 RPM. I think this is you can see the elliptical orbit here. And when the amplitude is very low at around 900 RPM or so, you can see that the orbit is fairly becoming a straight line. When the orbit is becoming a straight line, this thing on the full spectrum, you will see a equal amplitude of the forward and the reverse components there. Still, the rotor could be forward precision only. So coming back to this one, in the earlier case, we have seen the rotor whirling. So if this is the split critical here, so at this below this critical and above this critical, rotors must be exhibiting forward precision. And at this point of time, in between them, the rotor can be experiencing for a momentary time a reverse precision here. So when the reverse precision is simply happening, the orbit is turning into a very highly elliptical shape here. This is the shutdown data from a gas turbine. Here again, you see that it is the precision is reverse, but again, this is fundamentally coming because of a probe swapping only. Now, if I take an orbit at the operating speed of 3000 RPM, in the next slide, the filtered one, the direction of rotation is clockwise here. Okay. Now, if I look at the orbit here, normally, because if I assume that the orbit, the key phaser is looking at a keyway, so then the direction of the orbit will be from keyway, from the blank to the bright. So if I look the blank to the bright, actually the direction is opposite here. Unfortunately, I kept in the other direction. So blank and the bright, so it is having a reverse precision. So the orbit is rotating in this direction, whereas the rotor is spinning in this direction. This is what this plot is suggesting. But actually, if you go here and see this one, the plot is taken, the orbit is taken from this data here. As I told you, this is not a real reverse precision of the rotor there. This is because of the probes swapping only. Most of the cases, many of the cases have seen hundreds of machines, system one data there. People, for knowingly or unknowingly, the probes swap and the data comes up like this one here. So this is not nothing to be alarmed. Only thing is that you need to swap the probes at an opportunity time. This is from another machine there. While the machine is coasting down at the critical speed, where you can see here at the critical speed, you can see that the forward component and the reverse component are almost coming up the same magnitude. Still, this is the point of time when the orbit will look like a fairly straight line or a highly elliptical orbit there. And as long as the reverse component is smaller than the forward component, the precision will always be forward. Only at any instant of time, if the reverse component, while under this condition, it's slightly higher than that one, the forward one, that instant of time, the rotor is likely to exhibit a reverse whirl on the situation there. I'm going to slightly show you a little more information. This is the Bode plots from the shutdown of a gas turbine. And I'm going to show you the orbits with respect to this condition. When it is again the same way, we are going to look at a more closer look here. So coming back here, this is the 1000 RPM. This is the around 900, 890 or 900 RPM. And this is the 800 RPM, means high peak, low peak, and high peak here. So when the 1000 RPM is there, you can see that the rotor is rotating in the clockwise direction, and the precision is also from blank to bright. It is also here. This is a forward precision. Now, when the rotor is at 890 RPM, you see that it's like a straight line. And you have already seen on the full spectrum that the reverse component, the forward component are also exhibiting the same amplitude there. So this is how, when this is slightly reverse precision is likely to take place at this situation. When the rotor passes from 890 to 800 RPM now the machine again now has come to the forward precision here. This is the direction of the rotation of the rotor, and the precision is from blank to bright, and is again in the same direction that is happening there. So this is how the precision is going to help us to view the data. How the key phasor data is going to help us to identify the precision of the orbit, whether it is forward or forwards or reverse and all those things, and then helps us to identify what is happening on the machine there. So, dear friends, this is what I thought the short time. Of course, these are the subjects which can be spoken for days, understanding all these things there. So as the saying goes, Rome was not built in a day. A half an hour or a 1 hour discussions cannot completely give you a clarity on this one, but definitely this can set a starting point for those of you who are trying to understand this concept here. This could be a starting point for you to initiate your understanding of these things, and then refer to attend some good training programs or refer to good textbooks which are there on this concept here, or look at the real-time data from various machines there, which will help you to enhance your knowledge and get confidence in understanding these concepts there. So with this, I would like to thank you, all of you who are joined online, and you have given your valuable time for this webinar there. And if there are any questions session, I would like to, we'll have around another 10 minutes. So I'll be happy to accept your questions if you have any of them there.
Yes, sir. We do have few questions. Yes, sir. So, how does gyroscopic effect influence rotor precision?
Actually, initially I thought of including that in this topic here, but then what happened is that gyroscopic influence itself, the studying that itself is a big concept. It takes a little more time, maybe another half an hour or something like that, for me to bring in a few more slides and then explain them. Initially, I included them, but in the last minute, I excluded them from my discussion there. But yes, gyroscopic is another phenomena which is going to influence the rotor precision. So what is happening here is actually the critical in the critical speed map which I have shown you. I have shown you only a critical speed. Coming back here. Yeah. So I have shown you that as if it exists. For example, if I'm taking around 10,000 as my bearing stiffness, so this is a critical speed here. So if this is the critical speed of the rotor, this is the critical speed when the rotor is at rest. But when the rotor starts rotating and then starts increasing the speed, then this critical speed will split into two components by virtue of the gyroscopic action. And the gyroscopic action will split the critical speeds into two, one forward critical speed, then the other the reverse critical speed there. So for every rotor, for every mode, for example, a first critical speed, there will be a forward mode and a backward mode, backward whirl and a forward whirl. And the second critical speed, there will be a forward and this one here. And the other thing, good thing here is, most of the time, the backward whirls are not excited there. And then, So that's the reason our rotors, physical rotors, doesn't really experience this backward whirl while at the critical speeds there. Only the forward modes are experienced in the physical world. But I have read in some papers there where people have done the experiments, especially the lab experiments by the technical colleges. They have mentioned that on their rotors they have seen this reverse whirl is also getting excited by the residual unbalance on that one. To answer your question, yes, gyroscopic couple has an influence. It is going to split the critical speed, one called as the forward critical speed, which is higher, and the reverse critical speed, which is on the lower side of this one there. Because what is happening, gyroscopic is in certain cases, it is stiffening the rotor and then increasing the natural frequency, that is increasing the critical speed. And part of it, it is reducing the stiffness or it increasing the inertia of the rotor there, inertial mass. And then thereby reducing the stiffness of this thing and bringing out a lower critical speed there. So these concepts cannot be just explained in 10 minutes or 15 minutes there. And actually, these are the topics which are thoroughly discussed in rotor dynamics. Rotor dynamics by itself is a big subject. And this is also a part of the rotor dynamics there. Thank you for asking the question.
Yes, sir. We'll take two more questions. So what is the limit for glitch vibration amplitude? Is there any ISO standard?
There is no ISO standard, but if you are referring to most of these API standards, American Petroleum Institute standards, I think they try to give you, when you're trying to buy a steam turbine or a gas turbine or a centrifugal compressor or a pump or anything like that, they specify that I think they should be less than 10 or 15 microns. That is the most advisable one to get one, around 10 or 15 microns. And less than 1 mil, they say 1 mil is 25 microns, so it should be less than 1 mil. Preferably, if it is around 10, 15 microns, yes, we are happy to accept is the glitch there. But definitely, if it is more than 25 microns, that is more than 1 mil, you need to do something on the vibration data there. So you should compensate it in order to get a picture about the real vibration on the machine. Next.
Yes, sir. Why oil whirling shows in 0.4x?
Because that is not related. So whirling, what is happening? Okay. Why it is trying to show you something vibration less than, so okay, you can imagine right on yes. Okay. Okay. If this is the bearing housing and this is the rotor, let us say it is rotating like this, and then you have the oil sticking to this one here. So the oil film which is sticking to the rotor will have the velocity. If I'm looking at the velocity profile, it will have the velocity which is equal to the rotor speed. And then you can have the oil film which is sticking to the surface of the bearing, 0. So you'll have a 0 velocity here. So if you see the velocity profile along the length here, so here you have 0 and here you have maximum or V, whatever it is. So the average of this profile is going to be 0.5 V of the angular velocity here. So normally this is the average velocity of the oil fluid film which is whirling here. But most of the time it will not be exactly 5, but it will be slightly less than this one, 0.4. So practically you can see it between anywhere between 0.35 to 0.45 or so. So that's the reason you will have the whirling velocity or the whirling orbit is coming at these frequencies less than 0.5 there. Okay.
Yes, sir. We'll take one last question. After that, we have an announcement regarding our upcoming advanced turbomachinery course. Yeah. Okay. So the question is, rotor wheel is affecting oil wheel or they related at any time during machine operation?
See, it's not like that. See, rotor whirl is happening always. The rotor whirl is happening means rotor vibration is happening. When the oil whirl is coming, under normal circumstances, under normal circumstances, the whirling of the orbit, that is the whirling of the rotor center, is going to be mostly the synchronous whirl. It is going to be a synchronous whirl. Means the whirl frequency and the operating speed are the same. When you have your oil whirl here, now what happens is now the rotor starts whirling, but at a lesser speed, at a lower frequency there. So instead of completing the whirl cycle in one rotation, the rotor starts, it completes, it takes one rotation, second rotation, like that. So the total whirling action will take two rotations of the shaft here. So that's the reason the whirling action, that's why you're getting a subsynchronous component on that one. So the subsynchronous is coming because of the rotor whirling at that frequency there, because of the oil whirl frequency. As you can see that it is occurring at a subsynchronous frequency. This frequency is reflecting in the terms of the whirl like a subsynchronous one here. Okay.
Yes, sir. Thanks. Thanks for clearing all the doubts. I hope the doubts were cleared. So we'll answer those remaining questions through your mail. Yes, sir. We have an announcement from Navya now. Navya, you can share your screen.
Thank you, Ashok. So, hello everyone. I hope you all enjoyed the session and learned many things. So, thanks to all for joining the webinar and making it successful. So, here's the offer. Yeah, let me share my screen. Yeah. So, for our upcoming course, Advanced Turbomachinery, which is a complex subject by our Subbarao Ganti sir. So, we are planning to give away as the book of Fundamentals of Rotating Machinery Diagnostic, which is worth of 15,000 rupees as a giveaway to the participants who are joining for the Advanced Turbomachinery course. And we are also offering a flat 5,000 rupees discount to the only webinar attendees for the upcoming course. So hurry up and register for the course today, and you're going to lose this great deal since we have only limited seats. So thank you everyone for joining.